Welcome to our diffusion lab report. I'm Theo Durrett.
I'm Brandon Gucher.
And I'm Ben Mitchell.
In this report, we will analyze the results of our diffusion lab.
Our hypothesis states as the size of the beads increase, we expect the average velocity and average displacement of the beads to decrease, because the water molecule's impact on momentum will be smaller due to the larger beads having a greater mass. Our hypothesis is derived from the idea that momentum is conserved in a system.
In this experiment, we used an AMScope microscope with a magnification of 200% while recording a 1-minute video of 3 different sizes of beads. Before recording, the sample was shaken for 15 seconds to disperse the beads inside the solution. The recording didn't begin until 10 seconds after the solution was pipetted onto the slide. This ensured that none of the initial velocity from the solution being pipetted onto the slide was recorded. Using this process, we recorded the diffusion of beads of sizes 1.5, 2.5, and 5 microns. With the tracker program, each of the videos were analyzed in order to measure the movement and velocity of 5 beads from each sample.
On this slide, the results from the 1.5 micron bead test are displayed. The graphs on the right show the average results from the 5 1.5 micron bead trials. The data from these graphs was then used to calculate the average displacement and the average velocity for the beads. The average displacement for the 1.5 micron bead was calculated out to be 0.10188 microns, while the average velocity of these beads was calculated out to be 0.509 microns per second.
This slide shows the results of the 2.5 micron beads trials. The graphs on the right show an average of the 5 trials that we selected for each bead. What we get from this is that the change in displacement was 0.1249 microns below where it started, which is a higher distance than what we saw in the 1.5 micron beads. We also see an increase in the velocity at 0.5176 microns per second, which is faster than the 1.5 micron bead.
This slide shows the diffusion of the 5.0 micron beads. The graphs on the right show the average values from the data we collected using the tracker program. On the left are the calculations for each graph respectively. The calculations for change in displacement show the bead ended 0.2824 microns below where it started. This displacement is greater than that of the 1.5 and the 2.5 micron bead sizes. The change in velocity for this bead was 0.743 microns per second. This is a greater change than that of the 1.5 and 2.5 micron beads.
This slide shows the general trends in the change in displacement and change in velocity among different bead sizes. The trend line for change in displacement appears to be linear, while the trend line for change in velocity appears to be more exponential.
But what does it all mean, Basil?
In this experiment, we found out that our hypothesis proved to be completely incorrect. We hypothesized that change in velocity and change in displacement would go down as the bead size increased. This is completely opposite from what we collected in our data that shows that as the bead increased in size, it also increased in velocity and change in displacement. This is because as the bead increases in size, it also increases in surface area and thus has more contact with the water molecules, which change its momentum by colliding with it and transferring their momentum from the water molecule into the system that is the bead.
The system schema shows that beads and water are in their own system. When collisions occur, there is a transfer in momentum. Since the larger beads have a greater surface area, they experience a greater transfer in momentum due to an increase of collisions compared to the smaller beads.
This concludes our lab report.